Okay, so again, we are talking about single stage multi-machine systems, which is a special case of flexible manufacturing. So we're going to have a system, an automatic system that is going to be delivering these tools to each one of the extra tools to each one of these stations, and all the operations that are required for the part are going to be performed on that particular station. So here we have an example. Um, we have a tool carrier that is moving those tools from station to station. Those are loaded in this tool magazine. There are multiple uh, ink centers. And then also we have some RGB vehicles moving or the output of the components into the load and unload station. So this is one way that we can have this particular type of system design. Here we have another type of layout. It's a tool delivery system in a single stage multi-machine system. So we have some automated guided vehicles moving the parts between stations. We have a load, unload station, and simply storage. Um, each one of these squares represents a machine, and we have a tool carrier around, basically connected to each one of the machines, and that's what moves the tools from one station to the other. Okay, so in terms of the parts arrive according to the production requirement schedule. So you're gonna know when to start producing this type of part in this particular machine. That's gonna be based on your schedule. And a part transporter system handles the delivery of these parts, as we saw in those pictures, from the input station to the machine and from the machine to the output station. So we put them, we perform the operations, and then we get them back and put it back into the storage. A part cannot be processed unless the required tool is available. So you can imagine the amount of computer code that is needed first to provide the schedules that you need based on the requirements from your client. You have to come up with a good schedule. You're going to have to program a good algorithm to find what's the best schedule for the production that you are supposed to provide for your client. And then based on that, you're going to assign your production to these machines. You have to come up with another way to schedule the tools that you're going to need for each one of the machines at different times of the day. So this is a very interesting problem and very complex problem. And there's some of the tools that you learn in, for example, operational research that allow you to find those schedules. In terms of the tools, the required tools are specified by the process plan, and some tools are resident to the machine, so some of them will not move from the machine, while others are stored in a centralized tool storage system. So depending on the cost of these tools, you might be able to purchase one for each one of the machines, but if not, if some of them are very expensive, then you're going to have to share those resources. So that's why you might end up having a better cost by designing a system that moves the tools from station to station than buying a tool for each one of the stations. So that's when these part transporter, so we're talking about tools. right here. So in terms of the part transporter or transportation activity is minimal. Since in this type of system, you're gonna be visiting only one station. You perform all the operations in this part on that station, and then you remove the part and take it back to your storage. Vehicles are dispatched based on the parts arrivals and job completions. And you see why? You have to put those arrivals into your machines, or if you are producing those from scratch, then you need to assign those parts to each one of the machines. And then when they're done, they have to assign a vehicle to go find that job completion and put it into the storage. When vehicles are idle or when vehicles become idle, with one or more parts waiting to be transported. So that's for the parts. We're going to have also some tool carriers. So tool carrier handles the transport of tools to and from the centralized tool storage and the machines requiring the tool. One can also reallocate the tools when opportunities arise. So in terms of, as I mentioned, most important thing here in this type of system is how to design this schedule. So a schedule might look like this. You're going to have the machines, machine 1 and 2, and then you have a schedule for each one of the tools. So you have to find out what is just your production schedule for each one of the machines. Let's say you have, this is specifically for the tool. So tool 1 is going to be assigned to machine 2 at the beginning of the day. Tool number 2 is going to be assigned to machine number 1. But then when that one becomes available, you will send that to machine 1. Then you have the tool 1 available. You also have multiple tools. So you have to assign each one of the tools to each one of these machines throughout the day. You're going to have a schedule for the machine and also the schedule for the tool. And this again relates to the production schedule that you have for your system. So this is for single-stage multi-machine systems. Now, let's talk a little bit about just-in-time manufacturing, and this is one of the manufacturing systems that is very popular right now. It became popular when with Toyota. So basically revolutionized manufacturing from going from a line or production line like you used to see, for example, for vehicles that was designed, the first manufacturing line was designed by Henry Ford for Ford manufacturing. So just in time basically look at that design, which was used for several years, and saw that there were a lot of opportunities for improvement that type of system. That's some type of manufacturing system which having the manufacturing line, and you move the product from beginning to start, and you add components throughout the way. Works for some type of systems, but for other type of manufacturing system, that's not the best case. So just-in-time is based on observing the production line and finding better ways to do things. So let's talk about that. So this was developed more than 4 decades ago by Hono Taichi at the Toyota Motor Company in Japan. And just-in-time applies to all forms of manufacturing. So what they observed was that there were a lot of waste originally in systems that were based only on having the production line. So they find that by minimizing this waste, you can have a better quality on your product, and you can also have a better production output. So they divide the waste into the following 7 categories. The waste arising from overproduction. So if you are overproducing, what will happen is if you don't sell what you're producing, you're going to start accumulating those products into a warehouse. And every time you have a warehouse full, it means that you're paying for storage, and that's not good. That's a cost that you're incurring for your company. Waste arising from time on hand. So these are the products that are waiting to be moved to another station. Waste arising from transporting. Waste arising from processing itself. Waste arising from unnecessary stock on hand. And this one in particular is some companies, usually if you have to buy a component from a supplier, they will give you a cheaper price if you buy a high amount of units. So the more you buy, the cheaper the price. But if you buy, let's say 1,000 components and you only need 100, you're gonna end up having 900 of those components waiting to be used. So that's another waste arising from unnecessary stock on hand. Waste arising from unnecessary motion. And this can be applied to motion on the manufacturing cells or manufacturing production line. You might want to find the best way to use those stations, and also the movement of materials. And the waste arising for producing defecting goods. So I don't know if you know about the history of these car companies, but at some point Toyota was just a small company, and we have the largest automobile car companies were in the United States. They were Chevrolet, Ford, and Chrysler. And they were dominating most of the production of the cars at some point in the 1900s. So what they observed was that since they were very comfortable leading the industry, they started paying less attention to the quality of the product in terms of having effective components and that type of thing. So the way Toyota came into the map and started getting some popularity is because when they implemented this type of manufacturing system, they were able to produce very reliable cars. So these cars would last forever. They would not break down and so on. And also, so when they started comparing those reliability between automobiles, then they're starting gaining some of the market from these large companies. And right now they're just very competitive. So that's how they got to this point. So we talk about this waste arising from overproduction. This is a result of a production philosophy that's based on achieving economies of scale. So that's why we talk about buying more because it's cheaper. As the production load increases, the unit production cost will decrease. From the waste from time on hand, this arises when a worker tends only one machine. So if you only put the worker, he specializes on one machine, then you don't have the flexibility of moving that worker to other stations. Signing more machines per worker will reduce these weights. And a better layout may also contribute to maximizing the number of machines that one worker can tend. So when you look at the cell manufacturing design, that's one of the goals. You can have the worker move from one station to the other in a very limited space, but that needs a good design. And that also results in workers with multifunctional skills. In terms of weight from transporting, this comes from moving items over long distances. So this translates to what we've been trying to do with our algorithms. We have two departments that require a lot of movement, have a lot of problem moving from one department to the other. You want to be able to put those two departments as close as possible, so you can minimize the waste of transportation. Waste from transporting can be eliminated if the machines are placed close to each other. Yeah, the waste from processing, so an operator is unnecessarily tied up on a machine due to poor workplace design. That's also related to the design of the facility. So, for example, a pneumatic clamping device to hold work parts allows the operator to do more productive work. So, if you are able to design the station so that the worker can, for instance, not be trapped on doing one thing that you can do with having a holding or a type of machine that helps the worker, then that also relates to how you can improve the productivity of that station and of the worker. So in terms of implementing this philosophy, um, visibility can be attained by the following technique. And you want to provide that type of visibility so that everyone is on the same page. So if you go visit Samsung or any of these companies, you'll see that in the production area, they usually have boards saying this is the production, this is the goal, and so on. So electronic boards for quick feedback, pull systems, with Kanbans, and I think one of you asked me about what is a Kanban, and I provided a general explanation, but I have a video here that give you a better understanding of how this system. Sorry, trying to find the best way to show this. So originally, the way you produce parts or components or any type of product, you were buying things. Oh my God. So you were buying things and you were pushing the production down. So instead of you were producing to start basically, and then based on the demand, you were sell those products that you were having in your warehouse. What this thing just in time does is instead of having all these material storage on your company and all these product storage, final product storage in your warehouse, what it does is, depending on the requirement from the customer, let's say you put an order, based on that order, you're going to start pulling from your system what you need to get that order completed. So as you were seeing, you need one part to produce two parts to produce a component. Then once you produce that, you're going to send a signal to another area of your company saying, okay, I'm using these two parts. I have a space here. Please bring another part so I have at least one of them to produce the next one. So the system will send these signals. It will start pulling from different areas. And that way you can reduce some of the waste in terms of the storage, the working process, the material that you have in the area, and so on. So this is the pull system with Kanbans. Problem boards is also another tool. Color standards or colored standards. Containers, decentralized storage systems. Marked with designated areas for inventory and tools. As you saw in the video, that you have these areas that basically allow you to have only a certain number of units in that area, and that's it. Simplicity can be achieved with the pull system with Kanbans. Simple setup changes, certify processes, small lot sizes, and level production. Simple material handling system, multifunctional workers, and so on. So at the bottom of this slide, you have also a formal definition of what is a Kanban. What is the impact of number 3? Flexibility can be achieved with short setup times, short production times, small lot size, and Kanban cards. With flexible material handling equipment, and so on. Standardization can be achieved with standard tools, so everybody knows how to use them instead of having different type of the same tool, like one from Black & Decker, one from other company. You have all the same, so everybody knows how to use them. Equipment, pallet methods, containers, boxes, materials, and processes. And finally, organization is required for setup, cleanliness, work areas for the Kanban system, for the storage areas for tools, and for teamwork activities. Now, in terms of the impact of just-in-times in the facility, and this is something that I mentioned already, there are many concepts and techniques related to the just-in-time production system that impact the building design, the facility layout, and the material handling system, such as the reduction of inventories, deliveries to point of use, quality at the source, and better communication. So again, inventories can be reduced if products are produced, purchased, and delivered in small lots, so you don't have extra components waiting for you. Production schedule is very level. You have a good production system, a production schedule system that will balance the utilization of your machines, balance the utilization of your employees, and so on. Quality control procedures are improved if production material handling and transportation equipment are maintained. Products are pulled when needed and in the quantities needed. So that's why this pull system in just in time is very important. So if we are able to reduce the inventories, then we need space requirements are reduced. And how would that affect your layout? You're going to have more space for your facility. Also, if you're renting your facility, you might not need to rent as much space, so that will save some money to your company. Smaller loads are moved and stored, justifying the use of material handling and storage equipment alternatives for smaller loads. Storage requirements are reduced, justifying the use of smaller and simpler storage systems and the reduction of material handling. So, consequently, the building could be smaller, so that saves you money right there. A better plant and simpler plant layout could be used, and fewer handling and storage requirements might be needed. So by implementing this type of manufacturing system, you actually affect your facility design because you're going to need less space and you're going to have a better layout design at the end. So one more thing before we transition to our review for the exam. If products are purchased and produced in smaller lots, they should be delivered to the points of use to avoid stock outs at the consumption processes. And quality at the source means that every supplying process must record the next consuming process as the ultimate customer. So you are not focusing on the final product, you are also focusing on what your station is doing is higher quality so you can move that to the next station. And then in that way you keep the quality of your product. Each consuming process must always be able to rely on receiving only good parts from its suppliers. So to achieve the quality at the source concept, the following could be required. First, proper packaging, stacking and wrapping procedures for part boxes on pallets and containers. 2, efficient transportation. Handling and storage parts. A production system that allows the worker to perform his or her operation without time pressure. So you want to avoid the stress also in your facility. So that basically concludes the material for